My name is Andrew Jackson. I'm a geologist with Global Resource Investments, and I'm responsible for technical evaluations of the mineral companies and their properties that Global invests in. And I've put together this Ore Deposits 101 series of talks to help non-technical people understand ore deposits, how they form, how they're explored for, how they are evaluated and mined, and how the metals and minerals are extracted from the ore. The talks highlight some of the features of the main ore deposit types that you, as investors in the resource sector, may come across, and provide an introduction to the jargon that you will find in press releases put out by exploration and mining companies. There are 11 talks in the Ore Deposit 101 series. Each talk covers one or more of the major ore deposit types. This first talk is more of an introduction, and it covers plate tectonics and the fundamental role that plate tectonics plays in the formation of many ore deposit types. The talk will cover various ore forming processes, concentrating particularly on those associated with the cooling and crystallization of magmas as they rise through the Earth's crust. The second talk in the series will focus on deposits associated with mafic layered complexes, such as nickel, the platinum group metals, and chrome. The best known of these layered intrusions is the Bushveld complex in South Africa. We will also talk about kimberlites and their associated diamond deposits. The third talk will focus on porphyry deposits, those massive but low-grade deposits of copper, molybdenum, and gold that rim the Pacific Ocean. We'll also briefly discuss iron oxide copper-gold deposits, or IOCGs, in this talk, such as the giant Olympic Dam deposit in South Australia. The fourth talk will deal with vein deposits that form deep in the crust and host gold and copper. Most prolific of these are those found in the ancient greenstone belts, which provide a significant proportion of the world's gold production. The fifth talk will cover the so-called epithermal deposits. These all form at shallow depths and are hosts to gold and silver, and sometimes to lead and zinc as well. The Yanacocha deposit in Peru, which had reserves of 32 million ounces in 2005, belongs to this group of deposits. The sixth talk will be dedicated to Carlin gold deposits. The seventh will address the volcanogenic massive sulfides, or VMS deposits, which are formed by hot springs on the sea floor and are major copper, lead, zinc and gold producers. The eighth talk will cover the Witwatersrand gold deposits in South Africa, the biggest historical source of gold on Earth. The ninth talk will deal with the most common types of uranium deposits. And the last two talks don't deal with specific ore deposit types. Instead, they deal with exploration and the evaluation of deposits. The 10th talk focuses on the exploration process, what exploration tools are available, and how the exploration geologist selects which ones to use. It also talks about exploration strategies. The final talk in the series deals with ore resources and reserves, and once a mineral deposit is discovered, the process that is taken to evaluate it and reach a go or no-go decision to mine. Let's begin the first of the talks, basic plate tectonics and the associated mineralizing process. The formation of ore deposits is a hugely complicated process, with a myriad contributing variables such as rock and fluid compositions, temperature, pressure, pH, EH, structure, and time, all interacting to provide a host of different outcomes. In truth, ore deposit and exploration geology is much an art as it is a science. However, the basic concepts are very straightforward, and you don't need multiple degrees in geology to grasp these basics. Understanding some of the principles is best done over a beer, and you'll see why I say this in a little while. Everyone has seen diagrams of the cross-section of the Earth like this. The distance from the surface of the Earth to the center of the core is about 4,000 miles or 6,400 kilometers. The deepest drill hole ever sunk reached just 12.2 kilometers below surface, or 1/5 of 1% of the distance to the center of the Earth. So diagrams like this are based only on indirect measurements, including topography, bathymetry, observations of surface rocks, deep rock samples brought to the surface by volcanic activity, seismic, gravity and magnetic data, and laboratory experiments. Based on this indirect evidence, the Earth is thought to consist of three main layers. The central core is composed almost entirely of metal, iron, and nickel. The inner core is solid, the outer core is molten. The core is surrounded by the mantle, which is thickest of the three main layers. Although it is solid, it is hot enough to be able to flow plastically given enough time. The crust forms the outermost rind of the planet and is only 5 to 70 kilometers thick, averaging about 30 kilometers thick. It is largely solid, although there are molten or partially molten magma chambers, for example beneath active volcanoes. The thin crust is only half the density of the mantle, so the crust actually floats on top of the mantle. There is an old bumper sticker that says, "If it can't be grown, it has to be mined." And the vast majority of materials that are used to sustain mankind are ultimately derived from mining. And because the deepest mines on Earth, the Witwatersrand gold mines, are only about 4 kilometers deep, all the minerals used by man have to be obtained from the crust. The problem is that of the three layers, core, crust and mantle, the crust is the poorest in metals. So let's look at the metal content of that crust. This table summarizes the average crustal abundance of some of the most widely used metals. Figures are expressed in parts per million. So if the crust were homogeneous, each metric ton of crustal material would contain just 55 grams, or less than 2 ounces, of copper, 12 grams of lead, and a pinhead-sized piece of gold. Looking at it another way, to recover a 15-inch cube of gold, you would need more than 1 million truckloads of typical crustal rock, and I'm talking about big trucks like the one in the picture. Obviously, average crustal abundance is not going to cut it for an economic deposit. To make matters worse, if you were to try to extract these minute amounts of metals, most is tied up in crystal lattices of silicate minerals and would be virtually impossible to recover. Essentially planned Soviet Union economies were not particularly concerned about the cost of production. All that mattered was that there was enough volume produced to supply the state's requirements. But the free market economy doesn't work that way. Metals have to be produced for less than they can be sold for. So what concentration of metal is needed to make an economic deposit? Here are some ballpark figures. There are many factors that influence an economic cutoff, such as mining method, depth of a deposit, continuity of mineralization, metallurgy, and the current metal prices. However, these figures will do to illustrate my point. Few mines are profitable at a copper grade of less than 0.3% or 3,000 parts per million. For lead, few mines operate on a lead grade of less than 3% or 30,000 parts per million of lead as a sole product, and so on down. So how much upgrading from crustal average does nature have to do in order to produce a material that we might want to be able to economically mine? Well, looking at the right hand column, anything from 27 times in the case of nickel to 7,000 times in the case of silver. The conclusion is that nature must provide a significant concentrating mechanism before we can make any money on it. It's interesting to note that rare metals, such as gold, don't necessarily require more upgrading than more commonplace metals, such as lead, in order to reach economic levels. Now let's turn to how nature provides these higher concentrations of metals or ore deposits. In 90% of deposits, one single process is responsible for concentrating the metals. Partially melt a section of the crust or mantle. You'll see shortly why partially melting is important. Let the magma rise through the crust and progressively cool that magma to allow certain metals to be concentrated at various stages of this cooling process. So melt, rise, and cool. And we'll look at each of these processes in turn. To melt rock, you have to heat it or reduce the confining pressure of an already very hot rock. There are three main ways that melting of a rock occurs in nature. Firstly, by subduction. Secondly, by compression, by piling other rock on top of it or squeezing it horizontally. Thirdly, by injecting hot magma into it from below. And I'll go through each of these in turn in the next few slides. Starting with subduction. The thin rind of the Earth's crust isn't strong enough to withstand the convection currents in the underlying mantle, and it's broken up into a series of pieces or tectonic plates. In fact, there are about 15 of these plates, all being dragged in different directions and speeds by the convection currents in the underlying mantle. And the plates jostle one another like pack ice in the Arctic Ocean. In some places they move apart, in others they override each other, or simply slip past one another. In the map, the red and yellow arrows show this variability in direction and speed of movement. The length of the arrows is proportional to the speed of the movement of the plate in that position. Where plates diverge, mantle material wells up along the split and new oceanic crust is formed. Where plates converge, one plate is subducted under the other. Usually the denser oceanic plate is subducted under a less dense continental plate. As it sinks into the hot mantle below, the subducted plate heats up and eventually partially melts, with a lighter molten product rising up into the overlying crust to accumulate at magma chambers and to form lines of volcanoes where they reach the surface. The biggest subduction zone is the so-called Ring of Fire around the Pacific Ocean, and it's no coincidence that the Ring of Fire is also where most of the recent ore deposits are formed. Subduction is the dominant way of getting rock to melt. However, in addition to subduction, there are other ways of inducing melting, such as thickening of the crust, to increase the pressure and force the lower parts of the crust deeper into the hot mantle. There are two main ways to thicken the crust. You can pile new rocks on the surface, or you can compress it horizontally to form folds and thrust faults. Let's look at loading new rocks on existing crust. As mentioned earlier, the crust floats on the mantle like a raft or a boat on water. If you add a couple more people to a raft, it compensates for their weight by sinking a few inches and displacing more water. But because of the density difference between the crust and the air is much greater than the difference in density between the crust and the mantle, the base of the crust has to sink much more than the height of the added load in order to compensate. In fact, to achieve 2 kilometer increase in surface elevation, you can see the H in the diagram on the left, that requires the base of the crust to sink about 9 kilometers into the mantle. That's the distance labeled as root in the diagram. And 9 kilometers of sinking results in a temperature increase of between 250 and 300 degrees centigrade. and that's enough to start melting rocks that are already hot. So how does this thickening of the crust happen? Well, the most common ways are either the eruption and building of a large volcanic cone, such as Kilimanjaro in Tanzania, which rises about 17,000 feet or 5.2 kilometers above the surrounding plains, or by depositing sediments on a continental shelf, as has happened in Nevada prior to its uplift, which had many kilometers of sediment laid down on it. The second way to thicken the crust, as you can see on the diagram on the right, is to compress it horizontally, so that thrust faults form, allowing one part of the crust to be pushed on top of another. The last way to melt rocks without either subducting or thickening the crust is to inject hot magma from below. This magma injection usually occurs above a subduction zone, and it's the same principle as melting snow by pouring hot water on it. But unlike snow, which consists only of ice, rocks are usually made up of several minerals, each with their own different melting point. So if you heat a rock slowly, certain constituents or minerals within that rock will melt before the others. The first minerals to melt are commonly the felsic or pale colored, and most contain the highest percentage of silica. The remaining minerals, or restite, are commonly mafic or dark colored and relatively dense. Important for us, certain metals remain in the restite, and other metals prefer to separate into the felsic melt, which is generally less dense than the restite. This provides a mechanism that allows the first step towards concentrating metals to potentially economic grades. Gold, for example, usually partitions into the melt. So if a gold-bearing rock is partially melted to produce 20% melt by volume, that melt will be enriched 5 times in gold. We can detect these areas of partial melting in the crust even though they may be tens of kilometers below the surface, using seismic surveys. Seismics show them up as misty zones without any strong reflectors, as in this seismic section in Nevada. And notice the scale of it, maybe 80 kilometers across and the same distance top to bottom. These can be very huge volumes of rock involved. So much for the melting process. Now let's look at transporting this metal-rich melt upwards to where it can cool and deposit metals at potentially mineable depths. Like water dripping from a saturated sponge, the melt collects in any open spaces it can find. And because it is less dense than the surrounding restite, it starts to rise through the crust, slowly at first, but increasingly rapidly as it accumulates into bigger bodies and enters cooler rocks. Think of it as the hot wax in a lava lamp. You may ask, how can the melt rise through solid rock? And there are 3 main ways that this happens. At depth, where the rocks are hot and plastic, it simply displaces the rocks and passes through, shouldering the softer rocks aside and allowing them to close behind it, rather like wax pushing the oil in the lava lamp. If the rocks are too brittle to allow this, it can break off the rock above it and assimilate it, so it becomes part of the melt again, rather like an ice cube floating in a beaker full of hot water. Finally, near the surface, where the rocks are too cold or too brittle to allow either of these methods, it relies on finding or forming fractures and then flowing up those, rather like water leaking out of a cracked bowl. But as the magma rises through increasingly cool rocks, it loses its own heat, which in turn causes it to lose its buoyancy and to become more viscous. Eventually it cannot rise any further, and it accumulates in a large magma chamber where it starts to crystallize. Incidentally, magma chambers are often drawn as upside-down teardrop shapes, like the shape on the right of the image, but in reality they're usually flatter tabular bodies, like this one that has been exposed by erosion in the Sierra Nevada. Once the magma reaches the magma chamber and stops rising, it continues to lose heat to the surrounding rocks and the magma cools. Now we come to the importance of beer in understanding ore deposits. Beer is a great analogy for cooling magmas. Like beer, magmas contain varying amounts of dissolved volatiles, such as water, carbon dioxide, and sulfur dioxide. As magma rises, the pressure drops. The magma cools, and the volatiles separate and rise to the top of the magma chamber, just like gas bubbles in a glass of beer or a newly opened bottle of beer. This separation of the volatiles changes the pH or the acidity, the EH or oxidation, and the viscosity, etc. of both the gas and the remaining magma. But there isn't just a separation of volatiles and liquid magma. The magma also begins to crystallize. When an overcooled beer can is opened and the pressure suddenly drops, the beer immediately starts to freeze or crystallize. If you look closely at the picture on the right, you can see some of these crystals floating in the beer just below the foam. The same process occurs in the magma. So now our magma chamber has 4 different phases: volatiles, both as gas and a liquid, the main molten magma, and a mush of crystallizing minerals. As occurred when the rock was originally melted, each metal preferentially partitions into one or other of these phases, in other words, into the crystals, the gas, the liquid, or the remaining molten magma. So, for example, carbon in the form of diamonds and chromium in the form of chromite partition into the early formed crystals. Nickel and platinum combine with sulfur to form a dense sulfide melt that collects at the bottom of the magma chamber, like water in oil. Some of the copper may go into a brine solution and rise to the top of the chamber. Gold tends to go into the gas or aqueous liquids and also concentrate at the top of the magma chamber. So this partitioning provides the second critical process in concentrating metals to potentially economic grades. The magma chamber is usually not the end of the ride for the entire magma. It is generally simply a collection point on its way to being erupted from the volcano as lava, steam, and gas. Gas is less dense than magma, and so it tries to occupy a larger volume. So as the magma degasses in the chamber, the pressure in the magma chamber increases. Eventually the over-rocks are neither heavy enough nor strong enough to hold back that pressure, and the upper portion of the magma explodes upwards and erupts at the surface. This relieves the pressure, but is usually not a one-off event. It's followed by a quiet period, during which the gas and the fluids leak out as steam or hot mineral-rich water. Then the channelways clog with deposited minerals, and the pressure starts to rise again, and the whole process is then repeated. Over time, metals accumulate at various points in this system. Let's look at this more closely and see how this cooling process provides a very neat way of sorting out and concentrating the metals to a potentially mineable grade. The process of concentrating metals from the magma consists of cooling the magma or hydrothermal fluid so it deposits part of its material as solid crystals. These crystals are usually silicate minerals such as feldspars, pyroxenes, or quartz, which are of virtually no economic value. We need to dump these waste materials in the magma chamber and then to skim off the metal-rich melt or hydrothermal fluid. After this process is repeated several times, the fluid becomes supersaturated in the valuable metals and they begin to crystal out of solution, concentrated hundreds or even thousands of times to reach potentially economic grades. Cool, dump the dull stuff, skim off the cream. That's the process we're going to be talking about. Geologists broadly classify hydrothermal ore deposits according to the depth that they form at. So deep crustal deposits at 10 or 50 kilometer depth, mesothermal deposits forming between 1 and 10 kilometers depth, epithermal deposits usually less than a kilometer, and then the surface deposits right on surface. Let's take a look at where and how these ore minerals deposit in the system. Usually some of the first to form and the first to crystallize at the greatest depths are the mafic and ultramafic intrusions. And as they start to cool, they crystallize, and they crystallize out minerals such as pyroxenes and olivines and maybe even some feldspars. But those contain absolutely nothing of worth in them. So the metals that we do want are concentrated either in crystals themselves. They come out as later formed crystals, and for examples we could talk about chromium, platinum and diamonds forming in layered complexes and kimberlites respectively, or maybe they would combine with sulfur to form a sulfide melt. And copper and nickel are two metals that tend to do this in these intrusions. So we'll find nickel massive sulfide deposits, and we'll find copper-nickel deposits in layered complexes. As we continue up into a shallow area, we enter the porphyry domain. And again, as the magma continues to cool, it drops out crystals, this time usually of feldspars and quartz, concentrating the metals that we want into the remaining, either as crystals into melt, they may crystallize out later, to form tin and tungsten grisons. These are pretty unimportant deposits, we won't talk too much about those. But what is important with the porphyries are the metals which go into along to the gases and the salty brines that come out of them as they cool. Predominant among these are copper and molybdenum, and secondary with gold, iron and uranium. And the porphyry deposits and the IOCGs belong to this group of deposits, IOCG standing for iron oxide copper gold deposits. Rising up further into the mesothermal domain, further crystallization. At this stage we're normally talking, most of the feldspar has dropped out, we're talking about quartz and carbonate minerals dropping out of there, but again of no value to us in themselves. The metals that are of use to us concentrate further in the melt or into either the CO2 gases or the hydrothermal waters and brines that are coming off there. Copper, lead, zinc, gold, silver and lithium. Lithium's another odd bod like the tin and tungsten in grisons. Therefore it forms in pegmatites. It's not important, we won't talk about it again. But copper, lead and zinc and gold in particular are very important in mesothermal veins. Most of the greenstone deposits worldwide, which are big gold suppliers, are of this sort. Rising up now to the epithermal deposits. These are forming right in the roots of the volcanoes or very close to surface, within a kilometer of surface. They're still crystallizing out useless material or material that is useless to us, particularly quartz at this stage, and they're concentrating the metals that we do want either in the geothermal waters or the carbon dioxide gases. Particularly here we're talking about the precious metals, copper, silver and to a lesser degree mercury, forming epithermal deposits and kaolin deposits. We do get base metals such as copper, lead and zinc forming great deposits in this environment. The VHMS or volcanic hosted massive sulfide deposits are very important sources of base metals. Finally, when we get up to the surface and the surface rock is rained on and it starts to weather, getting oxygen coming in from the atmosphere and water from the rain, and those react with the rocks to break it down. And it can break down that rock into two forms. Either we can get particulate form that we want, particles, and the metals are gold, platinum, tin and titanium, and these are forming placer deposits, washed down in streams and concentrated by the water movement. Or the metals we want are going into solution, such as copper and uranium, and then being deposited downstream in secondary copper deposits around weathering copper porphyries in particular, or roll front uranium deposits. Now, each of the following 8 talks in this Ore Deposits 101 series covers one of these groups in this diagram. And that's the end of this one, except I need to summarize a few of the important points that we've covered. Firstly, few metals are abundant enough to mine economically without being pre-concentrated by nature. Average crustal abundance is not economic, and that's something which some promoters neglect to mention. The process of melt, rise, and cool is responsible for allowing 90% of deposits to reach economic grades. Partially melt by subduction, crustal thickening, or injection of hot magma. Partial melting provides the first concentrating mechanism. Then allow the magma to rise to mineable depths, either by displacement or assimilation of the rocks above it, or causing or taking advantage of fractures. Then cool the magma to allow the metals to concentrate into one or another phase. And this cooling and partitioning provides the second very powerful mechanism to concentrate the metals into economic grades. Most deposit types are simply variations on the same theme, with differences due to the source of the melt, the depth of differentiation, and the environment of deposition. The next talk will be on the deposits associated with the mafic layered complexes and kimberlite intrusions. These include copper, nickel, and platinum, and chrome, and primary or non-placer diamond deposits.